Terrifying announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a staggering revelation. They suggest that this cold world is on a potential collision course with Neptune. In any case, how could this happen? Also, what could be the consequences of such a colossal event? Are we witnessing a fascinating cosmic anomaly, or is there something more to this impending impact? Join us as we examine the possible outcomes of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet, mainly due to its unusual orbit, remains a subject of interest and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is alarmingly close to Neptune's. Tyson and Kaku are raising concerns about a potentially dangerous impact between these two celestial bodies, which could pose a massive risk to Earth. How is such an event even possible? Pluto's orbit around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. The intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unpredictable is its tilt, measured at 17 degrees to the ecliptic plane. Compared to other planets, Pluto's orbit is significantly more inclined, adding layers of complexity to its movement. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto is actually closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unusual trajectory. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elongated shape. The mystery deepened when astronomers realized that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit, despite these complexities, is evidence of the intricate nature of celestial mechanics. The three-body problem in space involves understanding how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on their starting positions and how they pull on each other. In Pluto's case, this problem reveals how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex way. Several key concepts help explain why Pluto does not collide with Neptune. Resonance and gravitational influence. Pluto and Neptune are in a 3:2 orbital resonance, meaning that for every 3 orbits Neptune completes, Pluto completes 2. This relationship ensures that their paths never directly intersect. Latitudinal libration. This refers to the vertical movement of a celestial body in its orbit. Pluto's orbital tilt means that even when it comes closest to Neptune, it remains positioned significantly above or below Neptune's orbital plane, providing an additional layer of protection from potential collisions. VZK oscillation. Named after 3 scientists, von Zeipel, Kozai, and Litov. This phenomenon describes how 3 celestial bodies, like Pluto, Neptune, and the Sun, influence each other gravitationally. This oscillation helps maintain the stability of Pluto's orbit over long periods. Despite Pluto's orbit appearing chaotic, these factors work together to keep it moving predictably over vast timescales. The three-body problem helps scientists understand how planetary orbits evolve due to gravitational interactions. However, numerical simulations in the late 1980s revealed that despite these stabilizing mechanisms, Pluto's orbit is, in fact, chaotic. Even minor deviations in initial conditions can lead to significant changes over millions of years. Nevertheless, the unique properties of Pluto's orbit have been found to maintain stability over incredibly long time frames, effectively keeping chaos in check. Recent simulations have provided insights into how giant planets like Neptune, Jupiter, and Saturn influence Pluto's trajectory. Neptune's gravitational relationship with Pluto plays a crucial role in its stability. Jupiter's gravity, 2, has a significant impact, helping to keep Pluto's orbit consistent for potentially billions of years. Saturn also contributes to this stability. These gravitational relationships prevent Pluto from colliding with Neptune or being ejected from the solar system. Without these intricate interactions, our solar system would be a far more chaotic and unpredictable place, with celestial bodies colliding or being flung into deep space. Understanding Pluto's orbit is crucial in evaluating the long-term dynamics of the solar system. The case of Pluto demonstrates how even seemingly unstable orbits can reach equilibrium through complex gravitational interactions. This highlights the importance of continuous observation and research to better understand our place in the universe. Exploring the depths of space often forces us to confront the unpredictable nature of celestial mechanics, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is strikingly evident in Pluto's case. Even slight changes in Pluto's position or velocity can drastically alter its long-term trajectory. Computational simulations have been instrumental in helping scientists decipher Pluto's movement in space. These simulations use advanced mathematical models to predict how Pluto and other celestial objects, like Neptune, influence each other gravitationally. By adjusting small details in the simulations, astronomers can see how even minor changes can lead to major differences in Pluto's trajectory. Back in the late 1980s, these simulations revealed something fascinating about Pluto's orbit. Even with stabilizing factors like axial tilt and orbital resonance, its path remains highly unpredictable over long periods. If Pluto's initial position or velocity is slightly altered, its orbit could look dramatically different over millions of years. Yet, despite this apparent chaos, Pluto's orbit remains stable over incredibly long timescales, suggesting that its journey around the Sun follows a kind of order, even if it appears chaotic at first glance. Predicting cosmic events, especially those involving chaotic or unpredictable orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainty. While numerical simulations provide fascinating insights, they cannot perfectly predict Pluto's distant future. Despite the unpredictability of Pluto's orbit, astronomers remain confident that a direct collision with Neptune is unlikely in the foreseeable future. The intricate gravitational dance between these celestial bodies, reinforced by orbital resonances and stabilizing influences from other planets, keeps Pluto's trajectory relatively secure. However, long-term simulations suggest that tiny perturbations, perhaps caused by passing asteroids, rogue planets, or even distant stellar influences, could gradually alter its path over millions or even billions of years. One intriguing possibility is that, given enough time, Pluto's orbit could evolve into a more chaotic state, increasing the likelihood of a near-miss or gravitational encounter with Neptune. Such an event wouldn't necessarily result in a catastrophic collision, but could significantly disrupt Pluto's orbit, potentially ejecting it from the solar system or altering its position in ways that have yet to be fully understood. The role of external forces. While Neptune, Jupiter, and Saturn play a crucial role in stabilizing Pluto's orbit, external forces beyond the solar system could introduce unpredictable variables. For instance, the passage of a nearby star through the Milky Way could disturb the Oort cloud, a vast region of icy bodies at the solar system's edge, sending a wave of comets and debris inward. Such an event could indirectly influence Pluto's orbit by shifting the gravitational balance within the outer solar system. Additionally, dark matter, an invisible yet dominant form of mass in the universe, could subtly affect planetary motions over extreme timescales. While current models do not suggest dark matter has a direct impact on Pluto's trajectory, ongoing research into its gravitational effects could provide new insights into long-term orbital dynamics. Could Pluto become a rogue planet? In the grander scheme of cosmic events, there is a remote but fascinating possibility that Pluto could eventually be ejected from the solar system altogether. If an external force, such as a passing rogue planet or a shift in Neptune's gravitational influence, were to disrupt Pluto's delicate balance, it could be flung into interstellar space. This would transform Pluto into a rogue planet, wandering the cosmos without a host star. While this scenario is purely speculative, it aligns with what astronomers have observed in exoplanetary systems, where rogue planets have been detected drifting through the galaxy. If Pluto were to be expelled from the solar system, it would join the ranks of these lonely celestial wanderers, carrying with it clues about the conditions and history of our own planetary neighborhood. The importance of continued observation. Given the complex and evolving nature of Pluto's orbit, astronomers continue to monitor its trajectory closely. Space missions like New Horizons, which provided humanity's first close-up images of Pluto in 2015, have significantly expanded our understanding of this distant world. Future missions equipped with more advanced observational tools could further refine our knowledge of Pluto's orbital stability and its interactions with Neptune. Furthermore, advancements in computational modeling are allowing scientists to simulate planetary movements with increasing precision. By refining our understanding of chaotic orbital mechanics, researchers hope to answer fundamental questions about the long-term fate of Pluto, Neptune, and the solar system as a whole. A cosmic perspective. Ultimately, Pluto's journey serves as a reminder of the delicate balance governing our solar system. While its orbit may appear unstable, it is in fact a testament to the intricate and self-regulating forces that maintain order amidst apparent chaos. The interplay of gravity, orbital resonance, and celestial mechanics ensures that, at least for the next several million years, Pluto will continue its icy voyage around the Sun, remaining one of the most fascinating and mysterious worlds in our cosmic backyard. Instruments for understanding and anticipating the future ways of heavenly bodies likewise feature the restrictions of our abilities to gauge these models. They vigorously rely upon the exactness of the beginning circumstances and the intricacy of the connections they recreate. Any little blunder or distortion can lead to boundlessly various results, making exact forecasts troublesome. Additionally, the turbulent nature of heavenly circles, like Pluto, serves as a sign of the steadily advancing and dynamic universe. While we've made huge progress in understanding space, Pluto's case embodies how much we still don't know about the universe. Understanding the gravitational impacts of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly affect the stability and trajectory of other bodies within the system. So, why are significant astrophysicists only now raising concerns about a potential collision between Pluto and Neptune? Despite all the complex forces working to prevent such an event, Tyson offers an intriguing perspective on the mysteries of our planetary system, particularly the fascinating case of Pluto. Known for advancing astronomy, Tyson sees the renaming of Pluto not as a demotion, but as a necessary adaptation to our evolving understanding of the many bodies orbiting our Sun. His approach to celestial mechanics is one of constant learning and development. Tyson sees the complexities of orbits, like Pluto's, as a reminder of how much there is still to discover in space. The allure of these questions, according to Tyson, is what makes astronomy so captivating. He deeply understands how space events and discoveries shape public interest in astronomy. He believes that events like Pluto's renaming or its orbital characteristics can enthrall the public's imagination and spark interest in the universe. Tyson, along with other scientists, warns the public about the possible risk of Pluto's erratic trajectory. After studying Pluto for years, he has raised concerns that the three-body problem could pose a significant risk of a collision with Neptune, an event he suggests may be long overdue. He emphasizes that such an impact could completely disrupt the balance of the universe and trigger catastrophic consequences, possibly even reaching Earth. If Pluto and Neptune were to collide, it would be a fascinating yet devastating event in our solar system. The collision would release an enormous amount of energy, potentially shattering Pluto due to its smaller size and icy composition. Debris from the impact could spread across the solar system, possibly posing hazards to other planets and their moons. For Neptune, such an impact could alter its atmosphere and potentially its orbit, depending on the specifics of the collision. Michio Kaku, a renowned theoretical physicist known for his work in string theory and as a popularizer of science, brings a unique perspective to this discussion. His views on the future of space exploration and the interplay between celestial mechanics and theoretical physics provide profound insights into the mysteries of space phenomena, like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a window into the future of space exploration. He believes that understanding the complex gravitational interactions and orbital mechanics of celestial bodies like Pluto can offer essential insights for future space missions. This knowledge can aid in exploring the solar system more effectively, predicting potential hazards, and even planning missions to the outer reaches of our planetary system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to the exploration of other celestial bodies, providing a blueprint for how we might approach and understand distant worlds. When discussing planetary physics, Kaku often highlights how celestial mechanics and theoretical physics are deeply intertwined. He believes that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated phenomena, but are connected to the fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, seeks to understand these principles at the most fundamental level. He often suggests that by studying the complexities of celestial mechanics, like Pluto's orbit, we can gain insights into the underlying laws of the universe. Like Tyson, Kaku has warned about the impending impact, linking it to his theories about the universe. If Pluto and Neptune were to collide, it would be a major event in astronomy, offering a rare observational opportunity that could intersect with string theory. String theory, a theoretical framework in which point-like particles of particle physics are replaced by one-dimensional strings, attempts to describe the fundamental forces and matter in the universe. A collision of such magnitude in the solar system could generate extreme conditions of energy and gravity, possibly creating scenarios where phenomena predicted by string theory could become observable. For instance, the high-energy impact could provide insights into the behavior of fundamental particles and forces under extreme conditions, key areas of interest in string theory. Additionally, the gravitational waves generated by such a collision could provide valuable data for testing predictions from string theory related to gravity and spacetime. These waves could carry signatures or anomalies that either align with or challenge string theory's predictions. While the direct impact on Earth would be minimal due to our distance from the outer solar system, the scientific implications of such an event could be enormous, contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit is a remarkable example of celestial mechanics at play, demonstrating both stability and chaos within our solar system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, particularly Neptune, highlight the unpredictable and dynamic nature of space. The three-body problem is not the only mystery of the universe we have yet to solve. Many other potential cosmic catastrophes are expected in the future. While the possibility of planetary collisions in space is truly fascinating, it cannot be entirely ruled out. The dynamics of planetary orbits can be affected by various factors, including gravitational interactions described by the three-body problem. In systems with multiple planets, such as the TRAPPIST-1 system, which contains 7 Earth-sized planets, these planets can exert gravitational pulls on each other, creating a rhythm or pattern in their movements known as orbital resonances.